Thanks to everyone for joining. We're going to give you an update on some work we've been doing at the Hub over the last several months. It's kind of a new topic for us, but it applies a set of well-developed tools to look at this question about what would be the implication of increasing the weight limits for RMC trucks. So, Harry, if you could go to the next slide for me on this. Yeah, so as we sort of already alluded to, but maybe just to give everyone a little bit of background on what the underlying challenge that we wanted to look at here was that under the current federal weight limits, which come in at around 54,000 pounds for a Class 8 truck, this in a number of contexts can lead to underutilizing capacity on those trucks, and in theory could even limit them by almost a third of what they're capable of delivering. And so of course that leads to higher costs, more more fuel use, but also create some other challenges which I think often get overlooked. If you could go to the next slide for us, Howran. Yeah, so ultimately, if we were able to make better use of that truck, right, then we would anticipate being able to make fewer trips. Of course, not in every job, but in many jobs, and so that, as I mentioned, could lead to lower overall costs and possibly and lower greenhouse gas emissions. We'll share with you sort of the results of looking at that specifically. But it also, we think, could have some real benefit for addressing a really persistent challenge the industry has faced, which is a driver shortage. It's something that almost every ready-mix producer in the industry reports about. And so if we can make better use of those trucks, we're also making better use of those drivers. So our question was essentially, what's the opportunity that comes from this? And specifically, we sort of asked the question, if we were able to shift from this limited load context to this more full load context, what would be the actual implications on operational efficiency, fuel use for those vehicles? But then we've looked beyond that, not just at the ready-mix producer implications themselves, but how they implement the transportation system as a whole. So how does that impact the pavements that these would drive on, and therefore the costs that would incur to the agencies that are charged with maintaining those? And then when we talk, Howran here put the system cost, and what we mean by that is, if our trucks are actually impacting the roads, then they would also be impacting the other vehicles that drive on those roads. And so we've developed a fairly unique set of models to let us answer those kind of questions. And so with that, I'm going to turn it over to the real expert here to tell you about how we looked at the question and then what it is that we found. So Howran, if you want to take it away.
Okay, thank you, Randy. My name is Harlan Lee. I'm working as a postdoc at the Hub. So I'll start from the methodology within this very important project. So first, as many of you already know, so we have our CSR pavement LC and LCCA2, which enable us to analysis a life cycle and a whole life cycle pavement environmental impact, as well as the cost or economic impact. So we also leverage the machine learning or AI-based pavement performance tools and modeling to predict long-term pavement deterioration, including cracking, rutting, and long-term IRI performance. Based on that, we're able to consider the whole pavement life cycle. In addition, as Randy explained it, we also include the trucks as the users of the pavement. We're not only talking about the RMC trucks, which we're focusing on, we're also interested in the other truck users. What is the impact of pavement deterioration to the RMC trucks as well as the other trucks? So based on that, we were able to consider the fuel use, pavement deterioration, long-term maintenance, and life cycle GHG and life cycle environmental impacts. Okay, so here's the research. So as we talk, we have the pavement life cycle assessment and our life cycle cost analysis, from the material production, pavement design, construction, use phase, maintenance, rehabilitation, as M&R, end of life. So what is scope within our pavement LC and LCC, which in embodied emissions include the raw material productions, pavement design, construction, M&R related emissions and costs, and end of life. And also, we're significantly considering the use phase emissions and use phase cost, including the pavement vehicle interactions as a PVI, related emissions, the pavement surface albedo impact, and the long-term concrete material carbonations. So also, as we talked, we include the use, which is the users of the road, the trucks, fuel LC, and LCCA. So as we can see in the bottom left, we're not only considering RMC trucks, but also all the other trucks. As we are observed, so the pavement vehicle introduction as the PVI include the two significant components, which were impacted by the long-term pavement deteriorations, which is the roughness and deflection related excessive fuel consumption from the truck users. So we also include the normal truck operations because potentially more loading by the RMC trucks, there will be fewer truck trips. So we include the normal operational truck fuel use and the related GT emissions and the cost. So as the overall, the societal impact or the whole system impact is the user pavement or the truck pavement infrastructure system. Okay, so to define a few loading scenarios, we will always start from the 0% additional gross vehicle weight GVW, which is the current federal limit, which is the 54,000 pounds, and we consider until 40% additional GVW, which is the total gross weight about 75 thousands of pounds of the RMC trucks. So the standard load here as the 54,000, we have about 6 cubic yards of payload of concrete material. And we'll assume there's 0% changes in GVW. Up to the 75,000 pounds, we'll have the fully loading scenarios, which compared to the 54, we're about 40% more gross vehicle weight, which is the we define as a fully loading scenarios. And for these scenarios, our concrete payload was increased from the 6 cubic yards to 11 cubic yards. So also we considering that is there any percentage of the trip saving because we're increasing the loading and the payload for the concrete materials. So as we assume initially, when this 54, we have 0 changes, which the trips, the RMC trucks are traveling 100%, nothing changed. But when we're having up to 40% additional gross vehicle weight, we're having about 50% reduction about the trips for the RMC trucks traveling over the pavement. Okay, so then we are doing the case study for a Pennsylvania rural interstate highway. So there are a few track volume and traffics. It's 37K of two-way ADT and about 0.8% of growth rate, 30% of truck percentage. And within those trucks, there are about 10% of RMC trucks, we assume, in this case study. 4-lane pavements, and also the analysis period life cycle is set up as 50 years. So now we are having our case study as a concrete pavement, which is the 10-inch joint plain concrete pavement at the top. Underneath are the 4-inch cement treated base. Underneath the 6-inch subgrade and subbase and subgrade. So for this Pennsylvania case study, so we have a default 3 MNR during the life cycle at the year of 15, 28, and 40 years, which are the dam grinding plus the full depth ridge placement for the concrete slab. So within this case study, we performed the pavement LC and LCC, as well as the truck LC and truck fuel LC and LCC analysis. So the first we observe is the truck fuels. So the top left figures is the format we will continue to represent our results. So for the x-axis is what we saw is additional GVW or additional loadings for the RMC trucks. So with 0, there's nothing changed. It's 54 thousands of pounds of the RMC trucks. up to 40% additional gross vehicle weight. So we can see that the y-axis is our unit as $1 million per land miles. So these are defined as all the RMC trucks operating or driving on this 1 lane miles pavement, because we're normalized as the pavement unit. So we use $1 million per land miles to represent the RMC truck fuels and truck fuel usage, and it's a relatively cost. So as we see that when there's no overloading, when it's 54, the federal limits, so we need about $4 million per land mile for RMC trucks traveling. But when we have the full loading scenarios, up to 40% additional gross vehicle weight, we can save about 32.5% of the fuel using for RMC trucks because of our savings from the trips of the more delivering per trip, because of the increased loadings from 6 cubic yards of the concrete material up to 11 cubic yards with 40% additional GVW. And we'll also consider the other trucks fuel use, as we can see that even though the RMC trucks start from $4 million per land mile, other trucks still dominate because they're 90% of the total trucks. But also we can observe that even though we are having the federal limit, no change, up to 40% increase of the GVW, there's no change of our other trucks fuel use at the relative cost. Because even though we have RMC trucks, we have a little bit more increase in the GVW, but there's no measurable impact for the other trucks fuel use and the relative cost, which is 0% impact. Okay, the second findings, we're investigating the impact of our pavement performance. As we just talked, we leverage the machine learning based on modeling to model the long-term pavement performance, including cracking, rutting, faulting, and error. So as we can see in the first figures, again, the 0%, 10%, up to 40% is our increase in the GVW, up to 40%, which is a full loading scenario, 11 cubic yards of concrete materials. We can see when we're plotting this pavement condition index for all the loading scenarios, we can see almost all the lines are overlapped to each other, and they're all corresponding to the 0%, which is no change. So which is no measurable change of a pavement deterioration when we're having the overloading up to, we'll have the full loading up to 40% for the RMC trucks. And also we investigated the infrastructure cost, which from the pavement LC and LCCA. So the infrastructure costs include the initial costs of the pavement design, construction, as well as the relative maintenance cost. So we have 3 maintenance, which the no change of our maintenance schedule, no change of our design, as well as our cost is always $0.53 million per land mile. Inform us that, okay, so even though you have RMC trucks have a fully loading with 40% additional GVW, there's no change of your infrastructure cost, which means that the planned design and maintenance schedule remains still adequate for this case study. Okay, so the third one is the total economic and the impact and the environmental impact. So first, I will have the total societal cost, as we just talked, is the pavement LCCA plus the truck fuel LCCA is the truck pavement or truck pavement infrastructure system. Okay, so as we can see that this has the different components from our total societal cost, including initial pavement design, M&R, which we just talked, which is no change, and the vehicle impact has a slightly change, but the truck fuels has much more change as labeled in the yellow part. Initially, when there's the federal limit, no change of our truck capacity, truck loading, truck GVW, there's about 22.9 million dollars per land miles for this whole system cost. But when we're keep increasing our RMC trucks GVW up to 40%, which is fully loading, so we can see the total societal cost decreased from $22.9 million per lab mile to 21.6. So overall, there's about 5.6% of reduction from the system level economic impact or the total societal economic impact. And also we consider the GHG emissions from our LCCA analysis for both pavement system and the truck views for both the RMC and the other trucks. So you can see that once initial, there's no change of our federal limits, which has about 78.8 kiloton of CO2 equivalent per lab miles. But when we keep increasing our additional GVW for RMC trucks, we have a keep decreasing of our life cycle GG per total system. So up to 40% when there's a fully loading of the RMC trucks, we are decreasing our life cycle GG for the GG emissions for the whole system from 78.8 to 74.25 total of CO2 equivalent per lab mile. That is equivalent about 5.8 the system level GG emission reduction or the total societal GG emission reductions. Okay, so what is the implementation for our policies or policymakers, stakeholders? So we can see that for this case study or this research, we heavily rely on the data-driven, the weighted regulations, which is perform significantly better when we're just limit our RMC trucks using the static thresholds. So when we're safely fully loading our RMC trucks, which means the 11 cubic yards of concrete material still within the drum capacity and still within the RMC trucks class 8 3 axles, the manufacturer design capacity. So when safely fully loading our RMC trucks, we can improve our productivity, cost efficiency from not only the fuel, but also the overall societal system level cost, as well as the whole sustainability of the pavement truck system and the whole societal benefit. So the policies could be adopted better performance-based limitations with the monitoring of the pavement and truck system for life cycle. Okay, so the takeaways from today's webinar will be like, for now, when we're having the 54,000 pounds of standardized Class A 3XO RMC trucks, so we may need more trips, and we may have a normal fuel consumptions if we have no change, if we do not do anything. It has normal or common pavement deteriorations and normal costs and normal GHG emissions. But when we're safely controlled our fully loading scenarios for RMC trucks, as we see in the right-hand side of the figure, it is a win-win. So first, we're saving the fuel use and the fuel use related to the cost and the fuel GHG emissions, about 32.5% reduction of the fuel use when we have the full loading of RMC trucks. And also compared to our pavement deterioration, they're resulting a comparable deterioration for long-term pavement performance, which emphasize that our current pavement design, current maintenance rehabilitation schedule still adequate for this RMC trucks full loading scenarios. And for the overall system or payments infrastructure system, we're lowering the societal cost up to 5.6% and GHG emissions up to 5.8%. Okay, so if you have any questions, so we're ready to answer. Thank you.
Thanks so much, Haran. And I think we have at least one question coming in, but I might kick it off a little bit by asking you a couple things about sort of comparing what you've done to previous work, and then maybe getting to think a little bit about what are some of the extensions or limitations. Yeah. Actually, no, let's go ahead. We could probably address this question that had come in. He's wondering if maybe we could be a little bit more specific about how the fully loading impacts the deterioration of the road. So I think that was like slide 10 maybe for you, the IRI curves there. And so what maybe I'm going to give a high level answer and then you kind of give some of the specifics of that how it ran. But I believe the answer is no change, right? So in other words, what we're seeing, and this results in, and maybe this is kind of a good jumping off point to a question I was going to have, which is how would you what's different about the analysis that you've done and other analyses that we see out in the literature, so in the scientific literature. But just to kind of first, before getting to that, let's talk about what the so correct me if I'm wrong, but so your analysis would suggest that if we had the same well, I'll let you address the sub point here, but this change to increase, allowing the trucks to run fully loaded, our models would suggest no change in the rate of deterioration for those pavements. So that kind of sounds probably a little surprising, right? So we have some trucks carrying more weight, but I think it comes back to one of the key differences in the way that you structured this analysis than what we've seen from others. So maybe you could first off make sure that I answered correctly there, and then secondly comment a little bit on that.
Right. Yeah. So, Randy, your brief answer is correct. So, okay. So in the literature, so we will observe the research existing for modeling the pavement performance for overloading scenarios. What they're doing is like they add additional axles or axle weight for the trucks, which means that they implicitly add the additional truck loadings or the freight which is not belonging to existing truck system, which means that those additional loadings or daily loadings or annual loadings are from arbitrary, which are not close to the practice. So what we model is like instead of increase the truck's weight or axle loadings for let's say single axle, tandem axle. So we're doing like simultaneously when we're increasing the axle loadings, single axle, tandem axle, but we're keep the total freight or the goods volume or its weight constantly each day, which
Mm-hmm.
means that we're not bringing additional weight or additional loading from arbitrary. So which means the total market requires or the market for the goods or the for RMC trucks for the concrete delivery keeps constant, which is that is our modeling strategy. To
Mm-hmm.
approaching that, so we're using the mechanistic empirical based pavement performance modeling, including the cracking, faulting area for the concrete pavement. So as overall, we will be able to predict long-term performance flexibly to adopt any extra loading increase, but keep the total freight or goods volume or the freight uh, practice close to the practice.
Mm-hmm. Yeah, so let me just make sure that I understood that. So the idea is in previous studies we might like imagine there were 1,000 trucks and they were carrying 1,000 units of load. And when in those previous studies, when they analyzed say 40% more, they are effectively analyzing 1,000 trucks carrying now 1,400 units of load, so 40% more load, or maybe 1,400 trucks. Either way, there's this increase in the total amount of what you were referring to as freight, right?
Yeah.
So that but you sort of thought that doesn't really make sense. We're delivering, just because I could put more concrete in the truck doesn't mean that we're going to be, you know, building more buildings or pavements or whatever. So instead, what you looked at was, let's assume we're delivering the same amount of concrete, but now we can do it with fewer trucks. So each truck is carrying 40% more, but there's, whatever, it's not exactly 40% less trucks, but it's whatever the inverse of that number would be. Now, I think it's important that there's some important details in what you said in there. It's it is true that a heavier axle load can increase sort of it, literally increases the burdens on the pavement and therefore could lead to more deterioration, right? But at least at this number of vehicles, this amount of change in loading, whatever that additional impact is offset by the fewer number of axles that are traveling over the pavement. Is that would you agree with that?
Yeah, that's correct. So when we're modeling the pavement performance, not only the axle loadings or truck weights is the impact factor, the number of trips, what we call in the repetitions of the axles, is another significant impact factor for the pavement deteriorations. So when we're having the overloading, we consider both the trade-offs in between. Because the RMC trucks are relatively small proportion of the total trucks, and total trucks is a small proportion of the total number of the vehicles. So overall, that's why we call the carefully or controlled full loadings for the up to 40%, we do not see measurable impact for the pavement deterioration changes.
Mm-hmm. So that kind of brings me to a little bit of a question that I was curious about, which is, what would you think is sort of the limits of that then, right? So like if we were to, are there, um, would we expect to see that differing if we were talking about many more trucks, or if we were talking about more than a 40% change, or what about even other pavement systems, pavement materials, or higher volume, lower volume types of roads? Like where I know that we haven't analyzed all of those cases, but what's your intuition of where you would maybe start to see that
Yeah, that's a
change a little bit?
yeah, that's a very good question. Actually, it's two questions. The
Mhm.
first is like we cannot arbitrarily increase the loading. For now, we have a controlled loading up to
Mhm.
40% additional GVW, but as we can just have extreme scenarios when there's a 100%, 1000%
Mhm.
increase, once loading on the pavement, it will deteriorate by one repetition of the trucks.
Mhm.
So that is the extreme scenarios.
Mhm.
And then we have to see, okay, maybe the current pavement design or maintenance is not adequate for these scenarios.
Mhm.
So, and also, if we extend to all the trucks overloading or actually full loadings, it might have a different, which I expect, like say, they may have slightly more faster deteriorations, and we
Mhm.
may have to adjust our payment design or the long-term maintenance schedule. So actually, we
Mhm.
just have a TRB paper accepted for next year January presentation. So we have extensive analysis for the all truck overloading scenarios. So I will welcome people to be there,
Mhm.
but I haven't know my schedule yet. And
Yeah.
yeah,
Okay. So everyone
okay,
should stay tuned for more specifics on that. But maybe you could kind of share qualitatively. So so what you're saying is, if this wasn't just all ready mix trucks, so it was all trucks, and
right.
then we would anticipate an increase in the rate of deterioration. So
Yes, in my
that would lead to sort of a negative consequence from this. How does that negative compare to the gains that one might see? Do we still see pardon me, do we still see a net gain in the system even if we were to expand this to all the trucks?
Yes, in my analysis for that extensive trucks full loadings, I do see the benefits because those benefit is from the fuel efficiency.
Hmm.
Because once all the trucks are fully loadings, we are significantly save the number of the trips for the trucks. Even though because the heavier trucks, heavier axle load have make us like a little bit faster payment deterioration. But when we're trying to schedule a little bit better maintenance, better design, we can still have the trade-offs. We can still see the net benefit from the whole system.
Nice. Um, what about so again, if folks have questions, please feel free to post them in the Q&A. Uh, I guess the other question that I thought would be good to get your reflections on, and I think I have a feeling this is one that you haven't specifically looked at, unlike the last one. Um, So maybe you could talk just a little bit about like why did we focus on such a specific case, right? The Pennsylvania, and then why is that a necessary thing to do in this context? And then maybe speculate a little bit about what the implications might be if we were to shift to other contexts, to other locations, essentially. Um, yeah. So first
Yeah,
off, like
there
why do we need to look at why does it need to be so specific when we talk about the case?
yeah, there's a bunch of reasons. So first, I have 5 years experience in Pennsylvania with PennDOT and the concrete pavement. So Pennsylvania start to build more concrete pavement. So automatically they are delivering more concrete using RMC trucks. So they are caring about the heavier RMC trucks, the behavior on the trucks, and also the pavement performance and the total cost and GG emissions. The second is like Pennsylvania. There is um, different types of concrete. So for us, we're interested in the interstate, but extensively we may do the low volume tracks, low volume roads, or etc. And the third thing is like when I was in Pittsburgh, people start to do the truck full loading, truck overloadings analysis. So we're like I try to kind of extend that analysis
Hmm.
here at MIT and to do more depth uh,
Yeah. So,
analysis.
Harry, let me before you answer the second part of my question, I wasn't I was probably a little confusing in the way I said it. I wasn't asking you like why Pennsylvania specifically, but like why do we need to have a very specific location in order to do this? I think that it comes down to like you didn't cover a lot of the detail that the what is the green curve which sits on top of the purple which sits on top of the yellow, the red, and the black dash curve um comes about from a very detailed analysis, right? Like maybe just comment a little bit about like what are the things that are important about the context that sort of drive that result there, right?
Um,
We need to know the specifics of the pavement section itself, right? In order to
oh,
model
right.
the
Yeah,
physics
this
of
case study
yeah.
is a real pavement existing in Pennsylvania.
Right.
So yeah, so we're doing that because we know it's the real pavement, and we want to see if we start to do the full loadings, if it's not a arbitrary assumption, so it's a real pavement. We want to see it's a real performance. If
Hmm.
we are trying to delivering more concrete material, building more pavement, back these policies to push these policies to a full loading, what is the real impact for this real pavement sections?
Hmm. Right. So you're able to capture in a lot of detail the physics of that very specific pavement by knowing a lot of those this basically both its physical description, like what the layers are, what the materials are, et cetera. And then maybe just real quick, we did just get a question come in, but maybe you could comment just a little bit. So say that we knew all of those details about, and you could change these locations, but I'm just going to arbitrarily pick a few, Florida, um, some Arizona, Colorado. Say we were thinking about, um, I know you haven't run the details of it, so I'm asking you to just speculate a bit. Would you anticipate the result to differ if we were looking in those contexts?
I will say quantitatively, yes, there could be some changes of the payment deteriorations, the fuel use because of the surface performance. But the I will say the total societal benefit still there. There's a net benefit. The
Hmm.
reason why, because for Pennsylvania, actually it's challenging because they have a freezing south, they have a snow, and it could deteriorate fast. But when it's a warmer place, the concrete pavement performance outstandingly. It could be even better than those cold regions.
Yeah. So at least for concrete pavements, this might actually be the toughest case.
Yeah, that's why we
Yeah,
select
probably
this
a
10th
different
state.
could be some different thoughts in around asphalt pavements might be something that we should maybe double check on. Let's take a look at, so we have this question here. So a lot of RMC trucks are built with more than three axles, including
Yes.
Pennsylvania as an example, apparently.
Right.
And so, which often you're going to have a four axle. Um, are we only increasing the loads for the fraction of RMC trucks that are three axles, or could we also look at implications for the, four axle trucks as
Yeah,
well?
that's a perfect question. So the reason why Pennsylvania is most using four axle because three axle limits 54. They want to carry more loads. They have
Hmm.
to use in this four axles. I believe it's about 70 or something. It's right actually close to our three axle full loading scenario in this case study. But we have this case study. We assume all the RMC trucks are three axles because we want to see that um, direct changes of that.
Hmm.
But in the future, we definitely can adapt any proportion of the three axles plus the four axles and the changes of the uh, three axle full loading plus full axle full loading scenario. Actually, I would expect actually more benefit because four axles they will have a larger drum or they will carry more loads even though like the three axles 54 the four axles that will has a larger manufacturing limit capacity so I
Hmm.
would expect more benefit actually.
Yeah. Yeah. And just to clarify one point on that. So like when we you meant, I just want to highlight a point that you made there. So we effectively have assumed that the four axles are three axles. And what the real implication of that is that we've tried to model the whole population of RMC trucks and their change. It's not like we only looked at, so if most of Pennsylvania's were four axles, we haven't just looked at the small proportion that were three. We tried to account for the whole population of RMC trucks there. So, but that's some great feedback. And if folks happen to know data on that, we could more accurately capture that split. It's certainly within the I think, we tried to keep this at a relatively high level, but there's some really deep modeling of the sort of specifics of the truck population and its impact on the pavement that Howran has developed to make this quite possible. So it's quite flexible to look at that kind of a thing. So um, maybe I'd ask maybe one last thing, and then which is, what would you say? What would you guess are kind of the key limitations here? What would be the things if there was more information that we would like to know, or what are the things that you'd still like to improve in what we're doing here?
I think it's something about the policy part. So
Mm,
we know the fuel tax for diesel and gas, and also the infrastructure tax. So we have limits. Um, I personally has a limit knowledge on that. And
mm-hmm.
also, if let's say the Pennsylvania 4XOs trucks, RMC trucks, so if like our audience can provide data for that, the fuel data and also the XO data and the loadings will be appreciated or
Yeah.
extend our to a more
Yeah, absolutely. I think that would be really beneficial. One thing, so you mentioned about the fuel data. I think that would be another thing we might put out a call for help on, which is that, to be honest with you, the fuel use information that's available in the literature is somewhat dated, and so it would be great to get more up to date information about the actual fuel efficiency. Oh, that does remind me of one small point I did want to make. On your key finding one, you had mentioned that the fuel efficiency improved by, I think it was
30,
32%
yeah,
or something like
30.
that. I did want to clarify for folks that we're using the term fuel efficiency here a little bit differently than I think is probably the most common. So, Howard, correct me if I'm wrong, but I think what you mean here is essentially the amount of fuel per cubic yard delivered
Yeah,
effectively, as opposed to kind of the more typical measure, which might be, miles per gallon is probably what, or essentially gallons per mile kind of a notion, right? So we are assuming actually that the that fuel efficiency actually kind of goes down as the load goes up, right? In other words, I'm using more fuel per mile because I'm carrying more, but I make it up because I'm carrying more, right? So I did want to make that one small clarifying point there. But it looks like we don't have any other questions coming in. So I want to thank everyone again. I think I think that Howran's work here, it's about a very specific topic, but points to some real opportunities for some meaningful policy change that could have both economic benefit, both to ready mix producers, obviously, but to the sort of economics of the system as a whole, as well as having greenhouse gas benefits. And so, thanks so much. I'm going to ask Andrew maybe to pop back on, tell you a little bit about the logistical details about distributing this, and maybe a hint about what other webinars are coming up. So.
Okay.
Awesome. Thank you very much. So again, thank you for your time and joining, your attention, and of course the discussion. So in terms of distribution, so we are going to share with you the slides as a PDF, and then also we're going to be posting this webinar on YouTube so that you may rewatch it and share it with other interested parties. So some of the other topics of interest that are coming up in the couple months include things like structural optimization, alternative fuels. We have an ever-expanding research portfolio here at the Hub, and we're excited to have you along for that journey with us. So with that, looking forward to seeing you again and wishing you a great day.